I want to diagram and we'll talk about with you the changes that can occur in blood volume and osmolarity, which could either occur to result in this same direction of a response or opposite direction. Um, this is blood volume also affects blood pressure. So this is also going to involve eventually a response from the cardiovascular system as well. It was a very integrative topic. So let's get right into the stimuli that can cause disturbances in these factors. So this is not talking about our body's responses yet, but just what things are we do um, that can cause changes in these two variables. The two variables being osmolarity. So this is in the ECF, largely determined by sodium concentration, right, in our extracellular fluid. We can have increases, normal or decreases. And then we have volume. We're talking about fluid volume, right? Fluid in, again, the ECF, um, primarily the plasma. And again, we've talked about decreases, well, actually decreases and increases in the responses that the cardiovascular system and urinary system have, because that alters blood pressure as well. Okay, so let's go through these. Let's start with our not changes in osmolarity independent of blood volume changes. So to get this way, we could eat salt, right? That would increase plasma osmolarity without changing blood volume. That's it. Our response, it's just the stimulus, right? Our response would be other things, but we're not going there yet. Okay, the opposite direction is a little bit less kind of something you might experience every day. This would be sweat loss. Sweat is hypotonic. So when we have sweat loss, we're decreasing osmolarity. But then we also, we're not losing fluid volume. So we're replacing the sweat with water. So we're losing, we're decreasing osmolarity. Could be other causes as well. I mean, drinking water would decrease osmolarity, but we have to be, in order to have volume stay the same, we'd have to be excreting out that water as well. So right, because this is isovolumic. So we have to be also losing that water. Um, okay, let's go down to decreases in volume. The first ones go from normal osmolarity. So in order to decrease plasma volume without changing osmolarity, we have to lose blood. This is going to be hemorrhaging. Here we're losing an isotonic fluid so that we don't have osmolarity change, but we have blood volume change. Okay. In order to increase osmolarity, we need to lose something like sweat that's hypotonic. So this is type of dehydration where we have sweat loss, could also be diarrhea, where we're losing excess water. So we're losing a hypotonic fluid, making our plasma hypertonic. And we've also lost fluid volume. Okay. Going over this way, another one's a little bit less intuitive, possibly. This is also could be dehydration. But in this case, we have dehydration followed by kind of an incomplete compensation. Um, So that we are obtaining fluids again. We have to, so of water. So we're replacing that sweat loss with water. That's going to decrease osmolarity, but not sufficient. We still have a dehydration occurring. So continued diarrhea, continued sweat loss, followed by continued drinking of water, where we're losing both fluids and decrease in osmolarity. Okay. Other way here. I'm going to draw this in blue because they're all types of ingesting. So first, let's do our normal osmolarity. Um, this would occur if we're ingesting isotonic fluid. Yep, right. Um, we would increase osmolarity as well if we are ingesting a hypertonic fluid, salt water. And then we're going to decrease osmolarity while increasing that plasma volume by ingesting just pure water. So, like distilled water is hypotonic. Okay. So we're going to look at the response of our body to these. Um, in order to do that, let's walk through what you need to know and already do know for a whole lot of this information. So let's walk through what happens to our body when we have decreases in blood pressure. And I'm going to do it in a different color because they're two different stimuli. Increases in osmolarity. There is a situation in which these two would happen at the same time. So, for example, if we had sweating, just a whole bunch of sweating, and we're not really replacing anything, that would cause both an increase in osmolarity and a decrease in blood pressure, right? That was that bottom right quadrant. We have just dish dehydration. Okay, so I'm going to draw this out. We're really answering that bottom right quadrant, but by doing that, we can understand the rest of them largely as well. Anything where the opposite happens, if we have an increase in blood pressure due to fluid volume, the diagram I'm drawing out would be the opposite response. Try to come back to that. Okay, so should be mostly review, but a lot of information. Low blood pressure is detected by baroreceptors in two locations. Do you remember where they are? One set is in the kind of central, so aortic arch and carotid body. These are detecting mean blood pressure. But there are also baroreceptors in the granular cells of the kidney that can call upon extrinsic regulation by producing renin. So let's continue going this way first. Renin triggers angiotensin 1, which is converted by angiotensin converted enzyme to angiotensin 2. Angiotensin 2 has 4 effects on the body. One is to target the hypothalamus, which produces ADH that goes out the posterior pituitary. ADH targets the collecting ducts in the kidney, of course, to reabsorb water. Okay, so that's one of the effects of angiotensin 2. The other one is there is a hypothalamic thirst center. So we're targeting the hypothalamus to increase thirst. So if there's water available, we'll drink it. Okay, third one is the adrenal gland. What hormone is produced by the adrenal gland in response to angiotensin? Aldosterone. Aldosterone targets the distal convoluted tubule to reabsorb sodium. Water is typically going to follow. Well, it is going to follow based on that signal. Okay, the last effect of angiotensin, I'm going to do in a different color because it is a response of the cardiovascular system. So this is going to be vasoconstriction. Does this make sense? Vasoconstriction in response to low blood pressure. Vasoconstriction causes increased total peripheral resistance. Right? Okay. Then we've got baroreceptors also targeting via the sympathetic nervous system three things: increased stroke volume, increased heart rate, and oh shoot, my other one I need to have go down to that total peripheral resistance. So I need to draw this line going down that way. Here we go. This is from the sympathetic nervous system. And actually, I do that in different color. So I'm about to switch colors anyways. So my cardiovascular system is what's responding with red. Go back to blue. This is sympathetic nervous system. Is triggering these three responses. And you know all about how that works. Those three responses, as well as the fluid volume, these are all going to increase blood pressure, right? So I could draw lines from there. This would also be called cardiac output, right? Those two variables. And then this is going to increase blood pressure by reabsorbing water. This is going to increase blood pressure by reabsorbing water. This is going to increase blood pressure, assuming we're drinking. Okay? Very comprehensive response to low blood pressure. Okay, then osmolarity. This is going to be a separate pathway over here. Increased osmolarity is detected by osmoreceptors in the hypothalamus. This is going to target, we're in the hypothalamus, we can target the two things that occur in our hypothalamus. So production of ADH to reabsorb water and increase thirst. You don't want the other responses, especially you don't want to increase in aldosterone because you don't want to reabsorb more sodium. Osmolarity is already high, right? Okay, so this is kind of a review of a lot, and then looking at these two different responses, which sometimes can go together. A increase in blood pressure or a decrease in osmolarity would just be turning the things off that they affect. So, right, so you could do a whole lot, probably yourself, to fill out this table. Okay, so to fill out this table, let's start with the one we just did, which is over here. Right, the diagram we just drew was an increase in osmolarity and a decrease in blood pressure. We drew both those out. So what did we have with that? We had increased ADH. I'm going to color code this. So let me switch. We had an increase in angiotensin. And we had an increase in the sympathetic activation of the cardiovascular system. I'm just going to write that. I'll put increased cardiovascular at this one place. I'm not going to write that out the other places. Okay, right? So what would this look like? Let's do ADH first. ADH is really, I forgot to say that in the previous slide, it's really responding to osmolarity quickest, most directly. So that's its main job. It's going to respond to increases in osmolarity regardless of what's happening in blood volume. We have an increase in blood pressure here. That's not a stimulus for ADH, but this is osmolarity driven solely. I mean, it's actually solely osmolarity driven as well here, but this is the one where that's in opposition, but it still is going to be an increase, even though the blood pressure volume signal is opposing it. You could say this one is like double increase. There's two different signals um, for it. So ADH responding primarily to osmolarity. Blood pressure changes can either amplify or um, oppose ADH. So that would be going over here. So over on the other side with low osmolarity, we're going to have decreases in ADH. So down here, this is the one that's also osmolarity driven. So low blood pressure would cause an increase in ADH, but osmolarity overrides that. Here, decrease in ADH because of low osmolarity. Here, really big decrease in ADH because of low osmolarity, as well as we really don't need it on for blood volume as well, or either. In between there with the normal osmolarity, here we would have a bit of ADH respond because of the low blood pressure. And here, the opposite, we have ADH slightly inhibited because of high blood pressure. There's no osmolarity to be the signal there, right? Okay, so osmolarity driven primarily with blood pressure being an influence if osmolarity doesn't change, or amplifying or opposing slightly in some cases. Well, in all cases, just some, yeah. Okay, aldosterone, that's responding to blood volume because that changes blood pressure. So it's going to be increased in all of these where there's decreased blood pressure. And it's going to decrease in all of these where there's high blood pressure. Yep. Um, this one, there's a small increase in angiotensin. It's not primarily responding to osmolarity, but it does help reabsorb sodium. So we would want to increase osmolarity a bit there. Same thing here, small decrease in I'm sorry, that should say aldosterone. And I did that all down there as well. And I did it on half of them apparently. All of these should say aldosterone. Um, really, it would be angiotensin also. It's just that's not the one that complicates. Ah, aldosterone, aldosterone. Okay, sympathetic nervous system is going to respond basically the same way as aldosterone, right? Its main job we're responding to low blood pressure. It's higher. So increase is color coded, so I'm not going to write that out. decrease, decrease, decrease. Um, Not much of a change. There can be small changes, but its job is mainly to respond to blood volume. Okay, one more hormone we need to talk about. What hormone responds to high blood pressure? There's one, ANP. So we're gonna have high ANP up here, low ANP down here. And you know, AMP also interacts with these other things. So AMP inhibits aldosterone. That fits with what we see here. AMP alters ADH as well. So it's interacting with these as well as decreasing blood pressure through cardiovascular system and other mechanisms. Okay. What I want you to be able to do, let me go here first. What I want you to be able to do is walk through those different scenarios and understand and be able to walk through the response. So I'm going to do one as an example. Here's one where you eat a large amount of salty popcorn with no fluids. So what quadrant is that we're talking about? Right here, right? Your increase in osmolarity and no change in volume. What would your body's response be? Well, first of all, we have increased osmolarity. We've increased sodium to increase osmolarity. Our body is going to respond. First, what's going to happen is our cells are going to compensate by moving fluid from the ICF to the ECF. So I should have a picture of that here. Here, increased ECF osmolarity. That's going to pull water out of our cells because we're maintaining ECF volume. That's what our bodies are trying to do. So it's to maintain, and because of the osmotic drive, osmotic gradient or osmotic drive is going to cause the cells to dehydrate or shrink. So this means we're going to have a increase in ECF volume because we've pulled water to dilute down the salts that we drank. We're going to have a decrease in ICF volume. Not a big deal, you know? But then what our body's going to do is increase thirst and increase ADH. This is going to allow us to obtain and retain through reabsorption water to be at to compensate for this high osmolarity. That will increase blood pressure, right? Because now we have more fluid volume. That fluid can move back into the ICF again eventually, but we also might have a decrease in things like heart rate, decrease in SVR, to compensate for that decreased water fluid volume.